Homologies of deep networks, presented by Thomas Gebhart.
Thank you. So, I'll be talking about path homologies of deep feed-forward networks, specifically path homology of deep feed-forward networks. This is a collaborative effort with Samir Chowdhury at Stanford, formerly the Ohio State. Myself at the University of Minnesota, Steve Huntsman at BAE Systems, and Matt Vutin, who's his intern at BAE and now at UC Berkeley. So hopefully you got some taste of why one might care about parameter topology within neural networks from Gunnar. Just going to state on that slightly more for the purpose of this talk. Especially there's been some recent work that read in the right light seems to imply that parameter, the actual topology, so the connectivity of these neural networks, is a main driver of their actual performance. So one of these, the lottery ticket hypothesis, which I'll come back to later and explain slightly in more depth, essentially the finding is you can take an over-parameterized, which in most cases is a usual architecture that we use for a problem. Take an over-parameterized network, you can find a very, very sparse subnetwork within that original network that when you train it from its original initialization of the parameter values actually performs just as well on the task at hand, or sometimes even better. There's also been some work from Geyer and Ha on weight agnostic neural networks. So they've shown that you can essentially find through some sort of like evolutionary algorithms connectivity structures within neural networks that when you apply random values to the weights, they actually perform fairly well at their task that they've been trained to, that the evolutionary algorithm has been trained on, optimized over. Random architectures is the same kind of idea, just at a higher level in the neural architecture search level. And again, neural architecture search, which is kind of a sub-region or a sub-interest of deep learning these days, is really topology-driven at this point. And a recent paper, it's hard to see the references, sorry. Recent paper has shown that if you include path information into neural architecture search, so like a convolutional block followed by a pooling block followed by a linear layer or something like that, actually gives you a better, allows you to search better over this architecture space. So hopefully I've made this point clear. Topological priors seem to matter in neural networks. Just so we're all on the same page, you can view a neural network as a directed graph, a directed acyclic graph. Oh man, he's not going to show up. Is he going to put it in the wrong? Oh, wow. Okay. Interesting. Can I save this as a PDF really quick?
Yeah, you can if you like.
It must be mapping it weirdly on the. Or else it's going to make it very difficult to read.
Just drop that desktop.
I don't know what that file was.
That's a PDF? Yeah, it just renders it the same way. It's not bad. That's not that bad.
Okay. We'll go back to PowerPoint.
And it takes a second or two.
All right, you guys get to read wonky math. So have fun with that.
There we go.
All right. Anyways, you can view these networks as directed graphs, essentially parameterized by these weight matrices that, in a fully connected network especially, give you the connectivity patterns. Directed graph. Convolutional and pooling layers can be represented similarly, just convolutional layers are going to be wider and sparser. So path homology, just a quick history. Somewhere around 2012 was kind of initially put forth by Gregorian et al. But more recently, Samir Chowdhury and Homology kind of brought it into the TDA realm by giving it a persistent flavor. And so we're using the notation from their work. Whew, that's fun. Okay, if we let G, and there's an X and an E hidden back there, be a digraph. Man, this is really hard. We can choose a P that's hidden behind that word define there. We can choose a P. This is a tuple that says x0 through xp. Essentially, we're just defining a path, a P path, right? A path of length P in our graph. We can, if we choose a field, K, which is conveniently hidden back here, we can denote the free vector space over these paths as this script A sub P. So here's just a quick example of what this might look like in a 3-node case. You have your paths of length 1, AB, BC, CA. If you look at script A2 here, you have ABC, BCA, CAB. If we were to apply our boundary operator from homology theory, we would get, let's say we're going to apply it on ABC here, we would get something that looks like BC minus AC plus AB. Right? Yeah, something like that. But notice that AC is not in this script A1 here, so we don't quite have a chain complex yet. So to do that, we define this boundary invariant, the set of boundary invariant p-paths on the graph G as a subspace of this original script A, the allowed path space, which is really just amounts to bookkeeping. So making sure that this boundary operator is taking you back into the allowed space of p-paths. So now we have a chain complex, and we can define homology as expected. In other words, the boundary, or the kernel, everything that's getting sent from the null space in dimension P, quotient by the image of the boundary operator 1 dimension up. Okay, so the canonical example here, which will get you almost all the way to understanding the associated paper, is this bifan motif. So you have this node A going to B and D and C as well. If we were to flip A and D, we get something that looks like this. Hopefully this should look familiar as a layer in a 2x2 neural, fully connected neural network. So if you can believe that, then you're most of the way to understanding the results in the paper. Here I've written the boundary invariant space. It's actually not any different than the allowed p-paths here, but you can see, for example, the reference for an example where you do need the boundary invariant space. Okay, so note that everything goes to 0, so the kernel is non-empty. So it has a non-trivial first dimensional path homology. This bifan motif here. Right. So our main theorem of the paper is if we let K denote our graphical representation of the network with layer widths n1 to nl. So this is the width of the layer at the width of layer 1, layer 2, layer L. We have a non-trivial reduced path homology in precisely degree degree L minus 1, and we can actually write down what that path homology should be. So we can essentially characterize the path homology of a fully connected network of L layers. We also say some things about the directed flag homology, which is like a directed RIPS complex, and it turns out it's going to look the same as the RIPS complex over the network. Okay, so some applications, since this is machine learning applications conference. So the lottery ticket hypothesis, written out, is given a neural network with sufficient parameterization for a task, with some probability there exists a subnetwork that when you train from the starting initial, the initial parameterization of that subnetwork, you get back a network that is massively reduced from the original network size. So this is really, you can think of it really as a form of pruning. But the way that you actually find these lottery ticket networks are you take a threshold on weight values of a trained network. And most of the time that threshold, for the examples I'm about to show, I used a 95% threshold. So the top 95%, or the top 5% of weight values in the network. Even a threshold as simple as that, and dumb as that, can give you a hugely pruned network. So here's just the background on this application. Train a fully connected ReLU network on MNIST and fashion MNIST, pretty simple. A somewhat simple but standard architecture of these layer sizes. So we're going to construct 50 lottery ticket networks. I'm being a little bit loose with the definition of lottery ticket network here. Some of them don't actually exceed the performance of the original networks, but they're fairly in line, as you'll see. We're going to compute the one-dimensional path homology of each layer of this 3-layer network. And then as something like a null hypothesis, a null network, we're also going to just take our original network and randomly remove 95% of the parameters. So here's some results. It's a little bit difficult to see. In the green, the ugly green color, you have the random network, so our kind of null network that has been 5% of the network's edges have been added to the network. Presumably, in all scenarios, this network has very poor performance on the data set. In red is our lottery ticket networks for fashion MNIST, and blue on MNIST. And along the bottom here, we have the path homology, so the first dimensional, or the rank of the path homology in degree P. So as you can see, in layer 1, the path homology is larger than one may expect, and we actually see differences between the two data sets. So again, this is counting that bifan motif that we're seeing in the network. That's really all this x-axis is counting. Layer 2, there's quite a stark difference, and we actually see significantly less of this bifan motif than what we would expect. And in layer 3, these are statistically different distributions, but notice that there's no tail. So one may interpret this as, by something like layer 2, this network is no longer crossing paths. It's no longer sharing information amongst nodes. So perhaps we've been pushed into some sort of independent paths along the network, maybe. Also on the bottom, I've included the expected path homology from the theory in the paper. I wouldn't read into this too much, as we're computing the expected path homology based on the nodes of the layers. And so actually you don't lose many nodes within the network when you're removing out edges, because there are a lot more edges than there are nodes in these big feed-forward, fully connected neural networks. So one may ask, finally, that whether there's any relationship to the accuracy of neural networks and this path homology, this bifan motif. And it turns out there maybe, I don't know. Here's a very simple regression accuracy on some linear combination of the layer-wise count of that bifan motif. And here you can see layer 2, again the one that I pointed out in the last slide, does show some significant p-value. You can read that however you want. The coefficient is fairly low, and also this is only 50 networks, 50 lottery ticket networks per data set, but hopefully this implies some future work of how one may go about investigating the relationship between topology and function of these networks. Here's some future work that I'll just leave up. Questions?
So I have a question. So when you measure the performance, is it all about the training or the test? I mean, sometimes regularization. We use we more prefer the small value for the some of the tolerance or the robustness of the model. Also, the one of the way make the model the robust, we using the dropout. So that means stochastically choose something and make it zero. Make the zero. That means if the something is compressed in terms of the structure without small number of the neurons or such things. In that case, some value should be shrink or the have to contain more than the other case of the values. In that case, I guess it could be increased. I mean, the value of the weight is a little bit larger than the regular size of the network. So that means it may lose some of the robustness of the things. The first question is that the performance is about the training or the test data?
Test.
Thank you.
All right, well, thank you.